So we're going to do a check of our program. It printed out this final velocity of the particle after it leaves the electric field. And it also gave us this time that it spent in the electric field. So Chris is going to draw a diagram of what we were modeling. And so we can also calculate using kinematics and what we know about forces and electric fields, what this final velocity should be based on physics. So since we did have that nice time measurement, we can start with, a fairly straightforward expression for what this final velocity should be. So if we're solving for the final velocity in the x direction, we can take the initial velocity in the x direction and add the acceleration it feels multiplied by the time it felt that acceleration or experienced that acceleration. And so the 9.1 that we got from our program, we can plug into here for this acceleration. The forces, for that acceleration, we can use Newton's law. So F equals ma. Here our F is equal to, how do you know it, like F sub E?
Sure.
Times, which is the charge of our particle times the electric field. And that equals our acceleration in the x direction times the mass from Newton's law. So if we want to solve for that acceleration, we divide by m on both sides. And so we have QE over m.
Right, now the nice part is that because E is in these funny units where it uses the, it's like force per elementary charge, things like that. So we can just use this as elementary charge and that as atomic mass units. So the 55.5, do you remember which particle that was for?
The proton.
Right, so charge of 1, then an atomic mass unit of 1. So Q is 1 and M equals 1.
Our E field was 5. So we just get 5.
Yep. So, and do you remember what our initial velocity was?
I think it was 10.
10.
So we have...
So I'm going to go ahead and run the numbers here.
Sure.
So it's 5 times what?
9.1. That was the time measured by the program.
Okay, that gives us 45.5 plus 10. 55.5. So exactly the same thing as we got from our program.
Oh, was the program 55.5?
Yeah, the 55 was 50. The program was 55.5. We got it right on.
Wow.
Yeah.
Wasn't even expecting it to be that good.
So the next part is a little bit trickier because the next part we have to, let's pretend like we don't know how much time has elapsed. Because in a real experiment, you can't just ask the protons how long they spent in the electric field. Excuse me, ma'am, how long did you spend? And so a lot of times we don't know what the time is. And so there's another formula that we can use in that case to try to, in that case, to still try to make headway. Do you remember what that formula is?
So we can also relate the square of the final velocity to the square of the initial velocity plus 2 times the same acceleration x, and now we're multiplying it by the displacement in the x direction.
Okay, so so we need to know over what distance the charge was accelerated, right? So you can correct me if I'm wrong, but this distance here, I believe, was equal to 300,
Mm-hmm.
right? Because I think this plate was 500 in x.
Mm-hmm.
That plate was 200 in x, and so 500 minus 200 is 300. Okay, so let's see if we can use that number over here to get the same result.
Yeah, so if we take the square root of both sides here, we have VXF. We'll take the positive solution.
I'm gonna get out my calculator here.
So for VXI, we have 10 squared plus 2 times the 5 we solved for before, and now 300.
So 2 times 5 times 300 is 2 times 5 is 10, so that's 3,000.
Mm-hmm.
10 squared is 100, so that's 3,100, and then the square root of that is oh goodness, 55.67. So about the same.
Mm-hmm.
So either way you do it, you end up with about 55.5 or so. So that works. That that works based on what we know. Now what we can do is we can try to predict what we will get if we change the charge or change the mass, things like that. So I believe that the activity asks us to increase the charge from 1 to 2, which is a little weird because there does not exist a particle that has an actual charge of 2 and a mass of 1. That would be like 2 protons, like no, not even 2 protons. It would be, anyway, if you have a magical proton that had a mass of 1 and a charge of 2, what would you get for the final speed? Now in this case, we don't know how much time it's spent in the field because we haven't run the program yet to figure it out. So what are we going to do?
Just use this method then.
Right, because it's still the same. We still know over what distance it's going to be accelerated. So how does the acceleration change if we increase the charge?
So if this Q goes from 1 to 2, right?
Mm-hmm.
While keeping the same mass, then we just have 10.
Okay. So then we can change this to a 10.
Mm-hmm.
So that's going to be 2 times 10 times 300. So 20 times 300. It's going to be 6,000 plus 100, so 6,100. And according to my calculations,
All right, that was smoother.
is 78.1. So that's our prediction. So we got to go into the code and see if that's actually true or not.
Mm-hmm.
But that's what we expect. And then what if instead of having charge of 2 and a mass of 1, what if it was charge of 1 and a mass of 2? Do you know what particle that is?
Charge of 1 and a mass of 2. So like that's our deuteron.
Our deuteron, yeah, that's right. So a deuteron is a proton and a neutron that are bonded together. And so the neutron, what's the charge of the neutron?
It's neutral.
Neutral, hence the name. And so the charge of the neutron is neutral. The proton has a charge of 1, so the charge is just 1. But the mass of the neutron is 1, and so 1 plus 1 is 2, and so the total mass is 2. And so instead of having acceleration of 5 or 10, it's 5 halves, which is 2.5.
Mm-hmm.
And so we can stick that into there. I think it's a little bit more elegant to leave it as 5 halves here because we're going to have a 2 there. Elegance is important in this business, friends.
It's very satisfying.
That's right. I don't often put on a tie, but I try to make my math as elegant as possible. Alright, so 5 halves times 2 is 5, right?
Conveniently cancels.
So 5 times 300 would be 1500. And then 100 plus 1500 is 1600.
So I don't think we need a calculator for this one.
Yeah, my phone was not working that great anyway. So 40 is our prediction for what the speed should be of a deuteron moving through the field. Cool. Well, let's go to the program and see if that turns out to be true.
All right.
Great.